Okay, got that going. All right, well, let's get started with the new material for today. Fortunately, not as prepared as I usually am. So I'll just have to look out the book, figure out what we're teaching as we go. All right. So the next section is on equivalence relations. So last time we talked about a relation. What's a relation?
Set of pairs.
A set of ordered pairs, right? Good. And we talked about 5 properties on a relation. What were the 5 properties we talked about?
Reflexive.
It could be reflexive. Let's focus on that. What was reflexive?
X is related to X.
Reflexive meant for all x in A, whatever the set is that our relation is defined on, x is related to x, right? Okay. What else did we have?
Irreflexive.
Irreflexive. What was irreflexive?
It's not related to itself.
Yes, that was for all x in A, x is not related to x. What else do we have?
Symmetric.
Symmetric. What was symmetric?
That if X is related to Y, then Y is related to X.
Perfect. If x is related to y, that implies y is related to x. What else do we have?
Anti-symmetric.
Antisymmetric. Antisymmetric. What was that?
For if X is related to Y, then does not mean Y is related to X.
If
X is related to y
and Y is related
and y is related to x, what does that imply?
to X is equal to Y.
X and y are the same thing. X is equal to y. Right? And then what's the last one we're missing?
Transitive.
Transitive. And what was transitive?
X is related
If
to
X
Z.
is related to Y and Y is related to Z, then
X related to y and y related to z implies x is related to z. Good. Okay, so now what is an equivalence relation?
X is equal to X.
This is a new term.
Yeah.
Equivalence relation. So, a relation R is an equivalence relation on a set A provided that it is reflexive,
Symmetric.
symmetric,
Antisymmetric.
and transitive. Just those 3. So we have a special name for relations that only are this one, and this one. You satisfy those 3 things, we call you an equivalence relation. Good? Okay, he gives some examples here of equivalence relations. We'll do same size. Let's do another one. Same last name and congruent. Question, which of these, well, we'll take it one at a time. The same size as relation. Is this an equivalence relation? So on the set of all objects, or on the set of all sets, however we want to think about, having the same size, is that an equivalence relation? Does every object have the same size as itself?
Yes.
Yes. So it's reflexive. Is it symmetric? If object X has the same size as object Y, does object Y have the same size as object X?
Yes.
Yes, so it's symmetric. If X is the same size as Y and Y is the same size as Z, is it the case that X is the same size as Z?
Yes.
Then it's now an equivalence relation. What about the same last name? Do you always have the same last name as yourself?
Yeah.
So it's reflexive. If you have the same last name as Joe, does Joe have the same last name as you?
Yeah.
Yeah.
Yes. If you have the same last name as Jack and Jack has the same last name as Jill, do you have the same last name as Jill?
Yes.
Yes. So those are all equivalence relations. Does he give any actual example problems? Guess we can make up some of our own really quick. Well, that's enough of the math. We'll get into concrete congruence relation here. Okay. So congruence modulo n. Defining a new relation. Congruent mod n. Let's see, how do I want to write this? Congruent mod n. Let n be a positive integer. We say x is congruent to y mod n, in parentheses. We say x is congruent to y mod n, defining a new relation here, provided that n divides x minus y. Okay, let's do some examples. Is 3 congruent to 13 mod 5? Yes or no?
Yes.
And we'll just write up a bunch of examples here.
What-
Yes. Is 3 congruent to 13 mod 5? How do we check this? What does it mean for 3 to be congruent to 13 mod 5? It means that their difference is divisible by that number. What's the difference of 3 and 13? 10, or negative 10 if we follow the way that we had it here. X minus y is negative 10. Does 5 divide negative 10?
Yes.
Yes. That's using the definition. Intuitively, how I personally think about it, and a lot of people come to think about this, is to instead think about, do they have the same remainder when we divide by this number? So go back to when you were first taught how to do long division in 3rd grade. If you were asked to do something like 103 divided by 10, you would have said it's 10 with a remainder of 3. Right?
Yeah.
Same thing here. If I asked you to do 3 divided by 5, if I asked a 3rd grader that, what would they say?
1 with the remainder of 2.
0 with a remainder of 3.
I was thinking the other way around.
Oh, right.
Yeah.
3 divided by 5. How many times does 5 go into 3?
0.
0 with a remainder of 3. How many times does 5 go into 13?
Twice.
Twice with a remainder of 3. They have the same remainder. Another way to think about it. But here's the exact definition. Here's the definition you'll have to use on tests, on your homework. That's just another way to think about it. So let's try another one. Is negative 7 congruent to, I don't know, 1 mod 4?
Yes.
Yes? How do you know?
No.
Because it's
Yeah.
divisible by 8.
What's divisible by 8?
4 divides 8.
Wait,
You're skipping a step. Walk it through. Negative 7 minus 1
Negative 8.
is negative 8.
Okay, but
Does 4 divide negative 8?
yeah.
no. Wait, yes.
Yes.
But-
4 times negative 2 is negative
But
8.
4 or 1 divided by 4 is 0 with the remainder of 1, and negative 7 divided by 4 is 1 with the remainder of 3.
How many times does 4 go into negative 7?
Oh. Hang on.
Negative 1 times.
Yeah. We're going to run into a problem here. Think about negative numbers. Maybe don't think about it that way yet. But we will run into this problem, so. If you require that the remainder is always positive. So say that you can't have a negative remainder. How many times does 4 go into negative 7? It goes into a negative 2 times with the remainder of 1. If you think about that.
Right.
But that's throwing you off. Perfect. Think about it this way and you're fine. What's negative 7 minus 1? Negative 8. Does 4 go into negative 8? Yes. Alright. Let's see. He has some tricky ones. Is 4 congruent to 4 mod 5? No, right?
That'd be
What's 4 minus 4?
0.
0. And does 5 divide 0?
No.
No, because there is no integer I can multiply 5 by to get 0.
Yeah.
Oh, there is! Stop relying on your intuition. Go back and think through the definitions. Sanity checks. So yes, that one's true. What about this? Is 0 congruent to 0 mod 5?
Yeah.
Yeah. It doesn't matter what x is. X is always congruent to x mod 5. For any number x you put there. Because what's x minus x?
0.
0.
And she's
And does 5 always divide 0? Yes. Okay. Let's try some mod 2 ones. Is 3 congruent to 7 mod 2?
Yeah.
Yeah?
Yes.
We sticking with it?
Yeah.
Yes? We good here? What about 100?
yes.
Is 100 congruent to 7 mod 2?
No.
No! How is he doing that so fast?
Because
It's
it's
an
not
odd
even.
number.
To not an even? Oh. So let's make this 1, 2, 8. And we'll make this 9, 9, 2.
Yes.
Yes?
Mm-hmm.
How are you doing that?
It's even. It's 50-50.
Right, they're saying that's an even, that's an even. What's an even minus an even?
An even.
An even. Is an even divisible by 2?
Yes.
Yes. And when I put a random odd here, they're doing the same thing. If I say 117, is that congruent to 999
No.
mod 2?
Yeah.
Yes. What's that?
Odd.
An odd. What's that? And an odd minus an odd is? An odd minus an odd is even?
Yeah.
Yeah.
Yes! An odd minus an odd is even. Do we need to prove that?
No.
Let's say x is odd and y is odd. Okay, if x is odd, then x can be written as 2a plus 1.
Mm-hmm.
And if y is odd, then y can be written as 2b plus 1. Right? So then x minus y, what's that equal to? 2a plus 1 minus 2b minus 1 is equal to 2a minus 2b, the ones go out, which is equal to 2 times a minus b, 2 times an integer. Even. Okay, an odd minus an odd is even. Is an even always divisible by 2?
Yeah.
Yes. So the mod 2 congruence relation, the congruence. Congruence mod 2, we'll say it that way, is the easiest one to do. All you need to check is see, do they have the same parity? Are they both even or are they both odd? Then it's true. If I instead replace this with an 8, then you instantly know it's
Not true.
false. Because an even minus an odd is going to be odd. And so it can't be divisible by 2. Make sense?
Yep.
Okay. So this is an operator, as weird as this one seems. This is one that's never going to go away. Not operator, sorry, relation. This is a relation that's never going to go away. You've got to get used to it, as weird as it is.
Why?
It's so useful. When we get to number 3, we use this stuff all the time. You want to understand the very basics of the encryption that we use for like your passwords and stuff, you need to understand the sync. It's like the very first building block of it.
What does mod mean?
It's related. So,
Modulation.
has anyone ever seen the mod operator before? Not this relation, but the mod operator. It just means give me the remainder. It's a common operation when you're dealing with integers. So 7 mod, we usually use a percent symbol for it. But then sometimes we just write out mod. Mod 5 is equal to 2. When I take 7 and I divide by 5, the remainder is 2. So it's a common operation in integer division. So you still just have the integers. Because remember,
Is it the same thing as subtract?
think about doing division the way that you're used to. If I say what's 7 divided by 5, what's the answer?
It's 1 2/5.
Yeah, you want to introduce rational numbers into this. What if I just want to stay in the integers and I don't want to introduce rational numbers? Do we just throw this operation together all together and say, oh, it's useless? Or do we want to somehow capture the fact that it's 1 with a remainder of 2? And so that's how we capture it with the integers. And to get that remainder part is what the mod does.
Okay.
And so it keeps you completely in the integers. And you can define both those operations.
Alright.
And that's where we'll use it, and we'll see a lot to do with that. Okay. So now let's prove that the congruent mod n relation is an equivalence relation. Now we've gotten familiar with it a little bit. So we're doing a proof that congruent mod n is I'm just going to use capital ER over and over again since we'll be saying equivalence relation over and over again. Okay, so we need to prove that that thing's a congruence relation. How do we do that? From here on out, when I give you a problem that asks you to prove something is an equivalence relation, sorry, I think I said the wrong word, but I meant equivalence relation. How do we prove something's an equivalence relation?
You show that it's reflexive symmetry.
Perfect. So that's what we start with. So first we need to make sure the congruence relation makes sense. The only way it makes sense is if we pick an n. So 1, let n be some positive integer. Our job is to show now that x is congruent to y mod n is an equivalence relation. And it doesn't matter what that n is, it's just some positive integer. So far we just say let n be a positive integer.
You did it 10 instead of plus.
Oh, thank you. And x, I don't know if we need x and y yet. Okay, 2. So now let's prove it's reflexive. How do we show it's reflexive?
Where x is equal, or n is equal.
We need to show that x is congruent to x mod n. So we need to say let x in z, comma, so pick some integer. Now I need to show it's congruent to itself mod n. Sorry, this congruence mod n only makes sense where x and y are integers. I don't think I specified that.
Okay.
We don't do it with decimal numbers. Make sense?
Yeah.
Okay, so let x be some integer. I need to show that x is congruent to x mod n. How am I going to show that x is congruent to x mod n? I need to show that n divides x minus x. And observe that 0 divides x, or sorry, n divides 0. Is that always true?
Yes.
N divides 0, which implies n divides 0, which implies x is congruent to x mod n, by definition. What does it mean to say x is congruent to x mod n? It means that n divides x minus x. Which implies it's reflexive. Okay, so we've shown that the relation is reflexive. Now we need to show that it's symmetric.
Okay.
So how do we show it's symmetric? We need to show that this being true implies this is true. Right?
Alright.
So 3. I've shown an implication, so I need to let the antecedent. So 3. Let x, y, and z such that x is congruent to y mod n. Right? If x is congruent to, and I need to show that this ultimately implies that y is congruent to x mod n. That means it's symmetric, right? Everyone understand the thinking? We're assuming the antecedent, and we're going to show that implies a conclusion. We assume x is related to y. We show that implies y is related to x. Okay, so what does it mean for x to be congruent to y mod n?
Means that x subtract y x subtract y. Oh wait, no. N divides x subtract y.
Perfect. It means that n divides x minus y. Now what am I trying to show? I'm trying to show that n divides y minus x. Okay? So what are we going to do now?
Minus is commutative. That's not true.
Thank you. Everyone understand what he just said? And how he corrected himself? Let's make sure we all understand that. That might be a tempting thing to do. Minus is not commutative. 5 minus 3 is not the same thing as 3 minus 5. Plus is commutative, minus is not. Good. So no, can't just do that. One down. Ideas?
You could times it by 1.
There's a tempting thing there. Multiply both sides by -1 somehow. Only problem, that's not an equation.
Oh.
Let's get it into an equation form.
Do you have to multiply both sides?
You can only do the multiply both sides if we're talking about an equation.
So just write it down.
So we need to get an equation from this. What does it mean for n to divide x minus y?
There exists an integer c.
Perfect. It means that there exists k in z such that n times k is equal to x minus y.
Yeah.
Right? Now we can multiply both sides by -1. So that gives me that n times minus k, I'm just going to put the -1 with this, is equal to, kids often get confused by this, so I'm going to write this out to the side really quick. But if I take x minus y and I multiply it by -1, what do I get?
Negative x plus y.
Or y minus x. So most kids trip up on that algebra, so let's make sure that algebra makes perfect sense. If I have a minus b, and I multiply it by -1, it's going to give me b minus a. Let's walk through that process and make sure that makes perfect sense. -1 times a is
Negative a.
negative a. -1 times negative b is positive b, so plus b. Now just change the order that we write it in.
Oh, okay.
Okay. So, I multiply this by -1 by just making the k negative, same thing. And I multiply this by -1, which is the same as just changing the order. Okay, now notice what do I have here? I have n times an integer is equal to y minus x. What does that give me?
It's divisible by y minus x.
Other way. Y minus x is divisible by n.
Yeah.
If n times an integer equals y minus x,
As divided.
that means n divides y minus x. Negative k also divides y minus x, but we don't care about that. What we cared about was, does n divide y minus x? So this gives me that y divides, or am I saying it wrong? Hopefully you understand what I'm saying. I don't know if I kept saying y when I meant n.
No?
Since n times an integer is y minus x, then n divides y minus x. And what does it mean for n to divide y minus x? What do we know then?
It's reflexive.
Don't skip steps.
Symmetric.
Means that it's the same thing.
It means that y is congruent to x mod n. Finish using your definitions. Don't skip steps. Now we have it. We started with x is congruent to y mod n. We got to y is congruent to x mod n. Wonderful. Which implies it is symmetric. Okay. Now we need to show transitive. If I remember right, he leaves that as an exercise for the student.
Just because it's the hardest one. You just want to do it.
Yeah. It's the leaders to the student.
Yeah, so leave it to the student. Oops, I've been doing that the whole time. You guys, you let me do that?
And you did it on irreflexive. You didn't add another on.
Yeah. Now it's just an N. Symmetric.
Ah! And anti-symmetric. Another M in there. You guys gotta catch me sooner. I'm thinking too much ahead as to what I'm doing.
You missed the unequivalence relation too.
What I miss?
Very
The
last.
other end,
Bottom right.
symmetric.
Oh, you're saying right there.
No.
Alright.
We get what you
Forget about it. Alright. So, equivalence classes. Why do we love equivalence classes so much? They partition a set. They partition a set. So what do we mean by that? Let's talk about partitioning a set.
What does partitioning mean?
Split it up into groups. You do this as a student body all the time. You partition yourselves up into sets. And you use equivalence relations to do this. For example, we could use the equivalence relation has the same last name. Right? That's the equivalence relation. It's reflexive, it's symmetric, it's transitive.
Okay.
What does that mean? I could take a set like the people in this room, and I could group them by has the same last name. So if A is a set of people in this room, so if A is equal to, we have Aiden, we have Phoenix, we have Deborah, we have Jeremy, we have Chandler. Perfect. I'll repeat initials. If that's our set, and we did the has the same last name relation, then we could create groups of you based off of, we could group you into this groups of people that have the same last name. So we could create a partition, call it B. Partition's a set of subsets, and let's see, Aiden, he'd be over here all by himself, poor guy. Phoenix and Debbie, they're over here. And then Jeremy and Chandler, like that. We just created a partition on the set. Things to note about a partition. We didn't bother with everyone who has the last name sitting in the class and put an empty set in here. So you don't bother with the empty sets, don't put those in. Right? So one thing to notice is we have no empty sets. Notice that everyone shows up somewhere in one of these sets. No one shows up in one of those sets twice. Right?
Yeah.
We could have done the same thing. We could have did the entire student body and partitioned them into the is in the same class as relation. Meaning what class you were taking this period. And we would do the same thing, right? So intuitively, that's what a partition relation, or an equivalence class does. That's what partitioning a set is. I keep jumping ahead. Because we're talking about equivalence classes first, before a partition. Shoot. They're the same thing, which is why I just confused myself. So now that we said that, we're not doing partitions quite yet. We're instead doing equivalence relations, or equivalence classes. What is an equivalence class? So we just really did an equivalence relation. That's one right here. What's an equivalence class? An equivalence class is a set of everything related to you. Okay? So let's say our equivalence relation is same last name. Alright?
No.
E.
Thank you. And we're doing it, A is all the students in this class like we had before. Then who are all the people related to Debbie under this relation? Debbie and Phoenix. So if we did the equivalence class on Debbie, that would have been equal to Debbie and Phoenix. If we would have done the equivalence class instead on Phoenix, it's the exact same set. Debbie and Phoenix. If we would have done the equivalence class on Chandler, we would have gotten Jeremy and Chandler. If we would have done the equivalence class on Hayden, we would have gotten Hayden. So you see how it's related to partitions. Equivalence class is basically which partition you're in. But we'll come back to the partition language in a second. So that's equivalence class, that's intuitively what it is. Now let me write out the exact definition to make sure it makes sense. So, equivalence class. What is an equivalence class? Let R be a relation on some set A, comma, and let little a be some member of big A. So in our example, R has the same last name, big A was a set of all students in the class, and little a would have been some random student in the class, like Debbie. Then, the equivalence class of A, or of Debbie, comma, denoted. We use this notation to specify the equivalence class. The equivalence class of A, denoted bracket A, is the set of all elements in A, big A, related to little a by R. Okay, that's one way to say it. Here's a more concise way to say it. Equivalence class A is defined to be the set of all the students X in A such that X is related to A. That's a more concise way to write it. You follow that? So if A was Debbie and capital A was all the students in the class, then the equivalence class for Debbie, if R has the same last name relation, the equivalence class for Debbie is defined to be the set of all the students in the class such that that student has the same last name as Debbie. Including Debbie. Debbie has the same last name as Debbie. Make sense there? Example, let R be has the same size relation defined on a set of set. Won't bother with that. Let's just go straight to the proof. All right, let R be an equivalence relation on a set A and let little a in big A. Then little a is in its own equivalence relation. Okay? So let's prove that someone's always a member of their own equivalence relation. And we almost get that for free. Probably shouldn't have erased this definition. Shoot. We'll just write the concise version of it really quick. What was the equivalence class of A? It was defined to be the set of all X in big A such that X is related to little a. Okay. Proof. Our proof is let R be an equivalence relation on a set A, comma, and let little a be a member of big A. Then little a is in its own equivalence class. Right, that's what we're proving. How would we prove that A is in its own equivalence class?
That it's an A.
Yeah, how do we show that little a is in its equivalence class? We need to show that little a is related to A. We need to show that A is related to itself.
As symmetric or reflexive.
Reflexive. Observe that R is an equivalence relation, which implies that it is reflexive, which implies what? That A is related to A, which implies what? That A is in its equivalence class. What is the equivalence class of A? It's the set of everything such that that thing is related to A. Is A related to A? Yes. So it's in there, by definition. Make sense?
Square box.
Yeah, square box. Let's see if he gives us a more complicated proof. Let R be an equivalence relation on a set A, and let A and B in A. Then A is related to B if and only if they have the same equivalence class. Okay, that's a more fun one. Let R be an equivalence class on A, and let little a and B in A. Then A is related to B if and only if the equivalence class on A is equal to the equivalence class on B. So we got to do an if and only if proof here. We've got to show that if A is related to B, then these classes are equal. And then we got to show that if these classes are equal, then A is related to B. Right? Am I losing you on this problem?
Well, which relation would it use?
So let R be some equivalence relation. We have no clue what equivalence relation. We just know that it is an equivalence relation on some set A. And we know that A and B are elements of A. So then we're showing that A is related to B if and only if they have the same equivalence class.
Oh, yeah.
So we need to show that A being related to B implies they have the same equivalence class. And we need to show that them having the same equivalence class implies they're related to each other. Let's go back to our example where A was a set of all students. We'll say that A is Debbie and B is Phoenix. Debbie has the same last name as Phoenix if and only if Debbie and Phoenix have the same equivalence class. What was the equivalence class for Debbie? The set containing Debbie and Phoenix. What was the equivalence class for Phoenix? The set containing Debbie and Phoenix.
Okay.
They're identical sets. That's what we're proving. So we need to show if they're related, then they're identical sets, and if they're identical sets, then they're related. Remember, if and only if means we got to do it both ways.
Mm-hmm.
So let's do it this way first. So we'll do this way first. So we're going to assume that A is related to B. And we need to get that these two sets are equal. We need to show that this implies that these two sets are equal. Remember that these are sets. How do I show that two sets are equal?
The X is in both of them.
That they're subsets of each other. I need to show anything in here is in here, and anything in here is in here. That's how you show two sets are equal. Right? So I need to grab a random element out of this set, show it's in this set, and then grab a random element out of this set and show it's in this set. So assume A is related to B, comma, and let X be some random element in the equivalent set A. I need to show that X is also in there. Right, if X is in A's equivalence class, what do we know?
X is in B's.
No, go back to definition. If X is in A's equivalence class, what do we know?
That X is related to A.
Then we know X is related to A. Look, if X is in Phoenix's equivalence class, we know X has the same last name as Phoenix. So if X is related, or if X is in A's equivalence class, we know that implies X is related to A. Right?
Yeah.
Okay? We know that X is related to A. We also know that A is related to B. Maybe come down here.
So we know that X is related to B.
Well, I don't know that I want to put that. So we know X is related to A, and we know already that A is related to B. What do those two together imply?
X is related to B, it's transitive.
X is related to B, because R is an equivalence relation, so R is transitive. So if you have X is related to A and A is related to B, you have X is related to B. Everyone following that?
Yeah.
Anything weird? We knew since X was in A's equivalence class that X was related to A. And we are assuming that A is related to B. That was already given. We're showing if A is related to B, then these two sets are equal. So since X is in A, we know X is related to A, and we already knew that A was related to B. Taking those two together, using the fact that every equivalence relation is transitive, then those two together imply X is related to B. Right?
Right.
Now if X is related to B, what does that mean? Means what?
That X is in B.
Then that implies that X is in B's equivalence class. What was B's equivalence class? B's equivalence class is the set of everything related to B. That's B's equivalence class. Is X related to B?
Yes.
Then by definition, X is in B's equivalence class. Follow through the logic one more time of what we just barely did. In other words, what we just barely showed is that A, here's what we showed. We showed if A is related to B, then the equivalence class on A is a subset of the equivalence class on B. That's what we've shown so far. We just barely showed that if A is related to B, then anything we grab in here is also in here. That's what we've shown so far. We grabbed a random element out of here, called it X. Since it wasn't there, X was related to A. We were assuming A is related to B, so X related to A and A is related to B implies X is related to B. What does it mean for X to be related to B? It means it's in B's equivalence class. So everything in A's equivalence class is in B's equivalence class. Now we need to do the other direction. And we need to show that everything in B's equivalence class is in A's equivalence class.
Okay.
Right? So, 2. Now, comma, let Y in B's equivalence class. What does it mean for Y to be in B's equivalence class?
Y is related to B.
It means Y is related to B. Right? So we know Y is related to B. What are we trying to say? We're trying to say Y is related to A.
Well,
So we know-
A
They
is
say B
related
is
to B.
related to A.
We know A is related to B.
But you gotta
Do we know that B is related to A?
because it's symmetric.
Because it's symmetric. Since R is symmetric, then we know. We also know that B is related to A. Right?
Right.
So now we have Y is related to B and B is related to A. Those two together give me what?
Y is related to A.
Y is related to A. And Y is related to A gives me what?
Y is in A.
Y is in A's equivalence class. It's not in A. A is an element. Unless you meant A the set, then obviously that was given. So then Y is in A's equivalence class, which what does that give us?
We had it last time.
Maybe put a period there, and then we can say 3. Then the equivalence class of A is equal to the equivalence class of B. That's what we've shown so far. So we just really showed that if A is related to B, then the equivalence class of A is equal to the equivalence class of B.
Yeah.
So we've shown the first direction here. We've shown if A is related to B, then their equivalence classes are equal. Now we need to do the other direction. So now we need to go this direction. We need to show that if their equivalence classes are equal, then they're related to each other. So now down here we assume that the equivalence class of A is equal to the equivalence class of B. Right? Alright, now we need to show that A is related to B.
Okay.
Then you just go backwards. X is in,
We know.
And this way is really easy.
Any element in A is also in B, and any element in B is also in A. They're related.
Pigs up the concrete. We're trying to show that A is related to B. How can we show that A is related to B? We need to show that little a is in B's equivalence class.
Okay.
So assume the equivalence class of A is equal to the equivalence class of B, comma, and observe that little a is in its equivalence class. Right? That's obviously true. We proved that with the previous proof. The first proof we did is an element is always in its own equivalence class. So I know that A is in its equivalence class.
and A's equivalence class is equals to B's equivalence class.
Perfect! A's equivalence class is equal to B's equivalence class. So then that gives me that
A is in B's equivalence.
A is in B's equivalence class. Fantastic. And what does that give me?
B's in A's equivalence.
No? What are we trying to show?
A is related to B.
And that gives me A is related to B. What is B's equivalence class? It's a set of everything related to B. So if A's in there, that's identical to saying A is related to B. And we're done. We did both directions. Good? This is one of those ideas that is so hard for students to wrap their head around the first time you come across it, and then every time after that, it just seems so stupid obvious. Because that's all we're really talking about is partitioning up into sets. And for some reason, it's really hard for you to get. I think it's just all the new, what's it called? Notation? That throws them off? I'm not sure. All right, next one. Let R be an equivalence relation on a set A. Oh, that's a homework problem. Next one, that's not a homework problem. Let R be an equivalence relation on A. So we got that. Let R be an equivalence relation on A, and suppose that the intersection of their equivalence classes is not empty. So basically I have the same setup here. Let R be an equivalence relation on A, and let A and B in A if the intersection of their equivalence classes. Will you turn down that heat?
Yeah.
Do one of you guys like crank that up? It's not equal to the empty set. Then they're the same equivalence class. What's it turn to?
What was that, 73?
You guys like a hot? All right. Here's what we're trying to show. So I need to show that this implies this. So one, assume that the equivalence class of A and B is not equal to the empty set. What does that mean? What does it mean for the intersection of two sets to not be empty?
There has to
That
be
there's
something
something inside.
That there's something inside.
Similar.
Inside what?
It's like
What's it?
the equivalent class of
Equivalent class of
Inside the equivalence class of A and the equivalence class of B. So there's something in both of them.
A.
Perfect. So if their intersection is not empty, there's something in both of them. So that implies that there exists some x in the initial set that we have our equivalence relation on, A, such that x is in A's equivalence class and x is in B's equivalence class. That's what it means for their intersection to not be empty. If their intersection isn't empty, then there has to be something that's in both their equivalence classes. If I have a set A and a set B here, and their intersection is not empty, then there's something that's in both, and we're calling that thing that's in both X. That's all we've done so far. Good? Okay, now what are we trying to prove?
That if
Here's what we're trying to prove. That their equivalence classes are the same. Or in other words, that this set is equal to this set. How do we prove two sets are equal?
Show that they're related.
So that they're subsets of each other.
Show that they're subsets of each other. It's always the same pattern. Grab something out of there, show it's in there. Grab something random out of there, show it's in there. Now, I shouldn't have said x here, because usually we like to use x as that variable, so we'll do c as the thing in both. You do with c?
sure.
Yeah, C works great.
Okay, so c is the thing that's in both those sets. So now I'm trying to show that there are two, that this is a subset of this, and this is a subset of this. First I'm going to show this is a subset of this. So I'm going to grab something random out of there. Let x in A. What does that give me?
X is related to A.
That gives me x is related to A. Good? Maybe before we go there, let's expand a little bit upon what this right here gives us. So that you can make these connections yourself rather than me just saying it. If C is in A's equivalence relation, what does that mean?
C is related to A.
That means C is related to A. Right? And it might also be useful to know, we also know that A is related to C. It's reflexive, right? So if C is in A's equivalence class, those two are related to each other.
And then C is related to B.
Since C is related to B, or since C is in B's equivalence class, we also know that C is related to B,
And B's related.
and we also know B is related to C. I'm not sure which of this information we're going to need to use, but just trying it out. That's what we know from these two facts, just making it explicit. Good?
Yeah.
Okay, so now let's start proving that they're subsets of each other. 2. Let x in A's equivalence relation. What does that give me?
Why don't you just prove it's transitive and then use the last proof? to prove
That X
that?
is related to A.
So then we have x is related to A. Where are we trying to get
That A is related, or
that x is related to B?
Right.
I'm trying to show everything in A's equivalence class is also in B's equivalence class. I grab something random out of there, I show it's also in there. Grab something random out of there, show it's in there. And we're done.
Okay.
How do I show? So x is something random out of here.
Why isn't B?
Huh?
So when you say no, why isn't B? And then,
We'll do y and b going back. But first, I grab a random x out of A,
Well, because C,
and now I need to show that that x is also in here.
because C is related to A and A is related, and C is related to B, then A is related to.
Yeah, we could also, I guess, expand upon this a little bit more if you want.
A is related to C and C is related to B, so A is related to B.
Right, so he's looking at these two together. He's saying since R's transitive, then we know from these two that A is related to B, right? So he wants to put that information up there as well. So we also know that. Okay, back down here, let x in A's equivalence class. That means x is related to A. We're trying to show that x is related to B. How can we do that?
Because X is related to A and A is related to B, then
Perfect.
X is
So
related to
we
B.
have x is related to A and A is related to B. Those together imply x is related to B. X related to B tells us what?
X is in the equivalent.
X is in B's equivalence class. Perfect. What did we just do? We showed that this is a subset of this. We showed that any random thing you take out of here is also in here. Now we need to show that any random thing you grab out of here is also in here. Right? So now let's do that. let y start out in B. What does that tell us?
That y is related to b.
That tells us y is related to B. We're trying to get y is related to A.
And b is related to a.
Right, we know A is related to B. Since R is reflexive, that also gives us B is related to A. So, using the fact that we also know that and B is related to A, those two together imply
That y is related to a.
that y is related to A, which tells us y is in A's equivalence class. And so A and B are the same equivalence class, they're same set. You can finish from there, right? Nice. Okay, did that. Corollary. Let R be an equivalence relation on a set A. The equivalence classes of R are non-empty, pairwise, disjoint subsets of A whose union is A. So we've proven all these pieces independently. It's just putting together the things that we know. And what we've proven is essentially that these have what we are going to call partitions down the road. Let R be an equivalence relation on A then the equivalence classes of R are non-empty, pairwise disjoint subsets of A whose union is A. This sounds like a mouthful, but we've already proven all these things individually. So let's make sure we understand the whole thing. Let R be an equivalence relation on A. So this is like has the same last name, where A is the set of everyone in the class. Then the equivalence classes of R are non-empty. How do we know the equivalence class is non-empty?
Because
It's not equal to the empty set.
How do I know that Debbie's equivalence class is non-empty?
Includes her at least.
It has at least her.
Yeah.
Take the equivalence class for that element, it contains at least that element. So it's non-empty. Pairwise disjoint, we just barely showed that with the previous proof. We showed that if they have any intersection, they're actually the same set. So we don't have two different sets with some elements in common. If two different sets have any elements in common, they're not two different sets, they're actually the same set. You with me?
Okay.
In other words, we show that you can't have the Hammonds and the Timpsons overlapping at all. They're pairwise disjoint, they're their own sets. And then pairwise disjoint, they're all subsets of A because they were all defined in terms of A. We took the set of all A such that some condition on A. So they were all subsets on A. And then how do we know that their union is A? How do I know that if I unioned up all the equivalence classes for each of you, I end up with the set A again?
A contains at each.
Because everyone's in an equivalence class.
Yeah.
You're all guaranteed to be in your own equivalence class. Right? So we've shown these conditions, and this is almost going to be the exact definition of what a partition is. So that ends the first section, and then the second section, very related. Second section is on partitions. Let A be a set. A partition on A is a set of non-empty, pairwise disjoint sets whose union is A.
Yeah.
Look at this definition here. Let R be an equivalence relation on A. then the equivalence classes of R are non-empty, pairwise, disjoint subsets of A whose union is A. Now I'm going to read what a partition of A is. Here's a partition of A. Let A be a set. A partition of A is a set of non-empty, pairwise, disjoint sets whose union is A.
Okay.
Right? So a partition. Let A be a set a partition on A is a set of non-empty pairwise disjoint sets whose union is A. Okay, and that's what I did the first time when I split you guys up based off of your last names. We said A was equal to everyone in the class. We have Jeremy, we have Chandler, we have Hayden, we have Debbie, we have Phoenix. And if we made a partition based off of your last names, then the partition P would equal the set containing Jeremy, Chandler, Hayden, Debbie, and Phoenix. And so it's like the set of all your equivalence classes is a partition. And so you can see these ideas are very closely related. Notice this was everyone who had the same last names as Jeremy's equivalence class. So partition, let's read it one more time. Let A be a set. In our case, A was the set of all students in this class. A partition on A, this whole set right here is a partition. This set of sets is a partition. A partition on A is a set of non-empty, notice none of those sets are empty, non-empty, pairwise disjoint sets, notice that no two sets have any elements in common, whose union is A. Notice if I take that set, union it with that set, union it with that set, I get the set A. Good?
Yeah.
All right. Partition, a bunch of examples. Let's do some concrete examples with just numbers. And you just tell me yes or no if it's a partition. So we'll do A is equal to the set 1, 2, 3, 4, 5, 6. All right. Let's do P is equal to the set, let's see, we have 1, 2, comma, 3, 5, comma, 6. Is this a partition on A? No, why not?
It's 4.
It doesn't contain 4. 4 doesn't show up in there anyway. Okay. Now is it a partition on A?
No.
No? Why not?
Pairwise disjoint.
Yeah.
It's no longer pairwise disjoint. This set and this set have some overlap. Right? Let's try another one.
No.
Are you sure?
Are you sure?
I mean, look, it's got 1, 2, 3, 4, 5, 6.
But it has an empty set.
But it has an empty set. So you can't have an empty set in a partition. Have to get rid of that, now it's a partition.
Doesn't everything already have an empty set already there? You just don't write it?
Yeah, but
No.
you can't have empty sets.
An empty set is an object.
Okay.
Having an object in your set is different than not having the object. So no, this set now does not contain the empty set. The empty set is its own object. Okay, so now we define a new relation, equivalence relation, which is in the same part relation. Here's what that looks like. We say A is equal with the P above it to B, and we define that notation to mean that there exists, they use P for the part, so you try and use fancy P for the partition. So P here is supposed to be our partition name. So there exists P, yeah, not very good. There exists P in our set of partitions. This is P and P such that A is in P and B is in P. So let's make sense of this really quick. So if we have our partition is equal to the set 1, 2, 3, 4, where A was equal to just 1, 2, 3, 4, then we could say that 1 is equal to, under that partition, 2. Or in other words, 1 is in the same part as 2. Because there exists some set P in our partition. We call the members of our partition parts. So that is a part, that is a part. So there exists a part in our partition containing those two elements. That's what that notation means.
So could you also say 1 is a partition of 1?
Yeah, we can say 1 is in the same part as 1. The way you read that is in the same part. 1 is in the same part as 1. 1 is always in the same part as 1. Okay, so now our job is to prove that this in the same part as relation is an equivalence relation. So prove let that be a partition on A, then that relation that is in the same part relation is an equivalence relation. So let's prove it's an equivalence relation. How do I show it's an equivalence relation?
If it's reflexive, symmetric, and transitive.
I need to show it's reflexive, symmetric, and transitive, right? So first, how do I show it's reflexive?
That's related to itself.
Yeah, I need to show that any random element in A is related to itself. So let X in A. What do I know?
If X is in A, then X
X is a part of X.
X is in A's.
Are we losing track of what the sets are? So A is like the set. Jeremy, Chandler, Hayden, Debbie, Phoenix. And now our partition is like the set Jeremy, Chandler, Hayden, Debbie, Phoenix. Right? So that's basically what we have. Now, we're doing that is in the same part relation. We're doing this relation. We're trying to show it's the equivalence relation. How do I show it's the equivalence relation? I need to show that no matter which of you I grab, you're in the same part as yourself. So, I grab one of you. I grabbed a random student. What do I know about that student? I know they have to show up in one of those parts.
Yes.
Right? Because a partition has to include every element in the set. What's the definition of a partition? Sets whose union is A. If the union is A, that means A, every element of big A has to show up in one of those parts. So I know that means that there must exist some part in our partition such that X is in that part. If you're in the class, you have to be in one of these parts. Right? And now, since you're in the part, you're definitely in the same part as yourself.
Okay.
So all we really need to do there is show that you're in some part. Since you're in some part, you're in the same part as yourself. So it's reflexive. So that gives us that this is reflexive. Okay. Now we need to show it's symmetric. How do we show it's symmetric?
That if you're related to them, they're related to you.
Yeah, we need to show that if x is in the same part as y, y is in the same part as x. So 2. Now assume that x is in the same part as y. What does that mean? That means that there exists some part in our partition such that
X and Y.
X,
Is in that part and Y is in
yeah, x is in P and y is in P, which gives us what?
X is in Y.
Which gives us, I mean, if you want to put the order there first, you can, but I'm fine with you just saying that gives us that y is in the same part as x. They're both in the same set.
So that means that is in the same part as commutative, kind of. It's symmetric.
It's not an operation. It's a relation. Students get confused by this over and over again. They're two very different things. A relation is something that we can call true or false. An operation spits back out whatever you're performing the operation on. 3 plus 5, true or false?
True.
Doesn't make sense. 3 plus 5, plus is an operation. When you apply an operation to numbers, you get numbers back. Relations are things we call true or false. We don't say 4 divides 8 is 2. No. 4 divides 8 is true. Right?
Yeah.
It's not an operation. You don't spit numbers out of that thing. Which means it's not an equation, so you can't be manipulating things. So this is something students get confused on all the time. This right here is a relation. It's something that we can call true or false. That's it. Okay. Anyways, so they're in the same part, which tells us that the relation is what? Symmetric. That is symmetric. Okay. So we show it's symmetric. Now we need to show it's transitive.
That X is related to Y and then Y is related to Z and they're both in P.
Right. We probably don't need to bother writing that one. If x is related to y and y is related to z, then x and y are in the same part, and y and z are in the same part. Therefore, x and z are in the same part. Therefore, it's transitive. I think you got it. Good? This is in the same part as, is basically talking about the exact same thing as our equivalence classes. Okay. Now, why did we bother with all this stuff? And how do equivalence classes help us? They help us count. So now we're getting back to counting. Never going to forget about counting. It all comes back to counting. Your counting hasn't gone away. And now we're going to count words. Let's see, the first word, let's just do word. Let's look at the letters W-O-R-D. So if you feel like we're completely switching gears here, we'll come back and see how it's related. All right, how many ways can I arrange those 4 letters? 4 factorial. Not 16. If those are my 4 letters, how many options do I have for what letter I put first? 4. How many for what letter goes second? 3, 2, 1. Okay. Now let's imagine that we have the letters word.
That's weird.
Right? If we have this word, how many ways can we arrange those letters?
5.
5 factorial. But now, suppose I say, how many ways can we arrange them so that they're unique words, including nonsense words?
What?
So,
4.
here's one way that you could arrange these letters. I could have first done W, O, then this R, then this R, then D, right? Or I could have done W, O, this R first, and then this R, then D, right?
So
But there's no distinction between those two. So how many unique combinations of letters could I get?
4 factorial?
I don't want to count that twice.
It's like 5 factorial minus
Is it 4 to the 4?
16?
Yeah, it's
4 to the 4, 4 factorial. Okay,
it's gonna be 5 to the 4. 4.
a lot of wild answers here. So what we could do is we could create an equivalence relation for all these words. So imagine we made all the possible combinations of those letters. There's going to be 5 factorial of them. Maybe we call this one R1 and R2 to distinguish them. But once they're arranged here, we don't want to count those as separate arrangements anymore, right?
Okay.
But I'm just going to label them so that we can see there's 5 things here. You with me so far? So imagine our set is all the 5 factorial ways that we can arrange those. Okay? And then I create an equivalence relation, an equivalence relation, which is they look the same when you ignore subscripts relation. Does this word look the same when you ignore subscripts as this word?
Yeah.
Then they'd be in the same equivalence class, right? How many equivalence classes, how many elements would be, so that's with one arrangement. Give me another arrangement. Give me a random letter.
R.
Which R?
2.
R2. So we have R2,
D2.
then what?
D2.
D.
O,
W.
W,
R.
R1.
R1.
R.
Now all we have left is RD.
Row.
So we could pick this one, but then swapping the R's around, this is the other way that we could have gotten that same arrangement, right? So for any arrangement of the letters, every equivalence class is going to be size 2, is what I'm trying to say here.
Yeah.
So we're creating equivalence classes on the set of all the ways that we can arrange those. So our set A is the set of all the ways that we can arrange these letters. So A is equal to W, O, R1, R2, B, comma, dot, 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 every possible arrangement we can have. How many are there possible arrangements?
5 factorial.
5 factorial. You've done this 100 times. Right? So we know the size of A is equal to 5 factorial. Right?
Okay.
Now, if we create a partition on A, where we do it with the relation is the same, looks the same when we ignore subscript relation, then we're splitting it into a bunch of these smaller sets of 2, right?
Mm-hmm.
You understand what I'm saying there?
Yeah.
So we could create a partition on this thing, P. P is going to be equal to, if we have this word, W, O, R1, R2, D, then it's also going to have, then it's also going to have W, O, R2, R1, D. And then comma, dot, 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 all the partitions, all the parts. Now notice that what we really are interested in is how many parts are in the partition. How many of these classes are there? That's what we care about.
Okay.
And what's the size now of this? Of our partition? What?
5 factorial divided by 2.
It's just 5 factorial divided by 2. No. 5 factorial divided by 2. Because look, if there were 100 people in this class, and I told you to pair off, how many pairs would we have? 50. We've got 5 factorial words, and now we're pairing them all off with their match. So now there's going to be half as many. And notice it's these matches that we're interested in counting.
Okay.
So how many unique arrangements are there of the letters? 5 factorial over 2. Because this arrangement and this arrangement really give us the same word. So we were counting the parts. We were counting these equivalence relations. We made up an equivalence relation for how those two were really the same somehow. Look at all their equivalence classes. So we took the size of the set divided by the size of their equivalence class, and we're done. Make sense? Let's try a little bit more complicated one. What if we had word? Or in other words, R1, R2, R3.
6 factorial.
So A, the size of all the possible arrangements, the size of A would be 6 factorial now, right?
Yeah.
But now, how many words, how many arrangements really give me this same exact word?
3.
3 arrangements?
No, it's 3 factorial.
It's 3 factorial arrangements.
6.
Because I could have word R1,
Oh yeah, you're right.
R3, R2, then D, W, O. So this is the ones that have R1 first. Then we could do the 2 that have R2 first and the 2 that have R3 first.
Yeah.
Or in other words, you can think about it as I have 3 options for which are to put here, and then 2 options for which are to put here, and 1 option for which are to put there. So if we were to split it up into its partition, each partition would have size 6, or 3 factorial. So how many unique combinations are there?
6 factorial is 1 factorial.
6 factorial divided by 3 factorial. If I have a group of 600 students, and I pair them off into groups of 6, how many groups do I have? 100. If I have 600 students, I pair them off in groups of 6, how many groups of students do I have? If we have 6 factorial words, and we pair them off into groups of 3 factorial, how many unique words do we have? 6 factorial over 3 factorial. You doing 6 times 5 times 4?
Quick math.
Yeah, it is quick math. 5 times 4 is 20, times 6 is 120. It's 120 words. Huh?
That was fast.
Yeah, you see how you can sound really smart by knowing how to count fast. All you do is know how to count fast, and you can say, oh yeah, the possible different arrangements with those letters, 120. Looks very impressive. All right. Let's try a more complicated word now. Oh, now we're in trouble.
1, 2, 3, 4,
Let's see.
7, 8.
We got I1, I2, I3. We got S1, S2.
I4. I4.
Oh, thank you. I4. We have S1, S2,
S3.
S3, S4, and we've got P1 and P2.
And M1.
And then it's just by itself. Okay, so first off, what's the size of A of all our possible arrangements of those letters?
However many letters that is.
5, 6, 7, 8, 9, 11.
11 factorial. Wonderful. Now, if we were to split this off into these equivalence classes, where different arrangements really give us the same word, how big is one of the equivalence classes going to be? How many ways can I get this exact same word?
1, 2, 3, a lot of ways.
Let's just write it. And how many options do I have for my first I?
4.
4. How many options for my first S?
4.
4.
3.
How many options for my second I?
3.
How many options for my second S?
You
Skip
missed
that.
your
Second
second
S.
S.
It's 4.
But it's still 3.
Alright, so we did first I, first S, second I, right?
Yeah, so
Which
it's
is 3, 2.
Third S,
2,
fourth S,
1, 2,
third I,
2.
first P,
2,
second P,
1,
last I.
1.
So you see, we had in here, if you just look at the I's, 4 times 3 times 2 times 1. And if you look at the S's, we had 4 times 3 times 2 times 1. And if you look at the P's, we had, 2 times 1.
Yeah,
No,
no, it's 2.
You have two.
that's I.
It's 2.
Oh, did I mix it up? Oh, this is the first P.
Yeah.
Okay. So, if we were to write this out, the other way that we could have just written all this multiplication out, this would have been the same thing as, how many I's do we have? 4? 4 factorial times, how many S's?
4 factorial.
Times,
3 factorial.
2 factorial.
just 2 factorial, right? And so, our answer now is how many unique arrangements? It's 11 factorial all over
4 factorial.
4 factorial times 4 factorial times 2 factorial.
What about the n?
Interesting.
Oh, never mind.
There's only one n, so that doesn't change anything. Good?
Yeah.
We can leave that at that. And the last one's just accounting proof to prove that our method here always works. It's just going to be really wordy with the same intuition.
We know it does though.
So, what's the intuition here? We took the size of A, all the possible arrangements, divided it by the size of each equivalence class, and that gives us the number of equivalence classes, which is what we're interested in. And that's what the last proof is about. Okay, so that's it for lecture. Go ahead, take a break, and then we have the rest of the class for homework and whatever else you want to go over.